good day or good morning. We see you. So just a sound check.
Okay, so I saw you again. Okay,
Yeah.
so your meeting is going on.
Your video and audio is working perfectly. Thank you.
Okay.
Good morning. Can you hear me well?
Yes, Victoria, we
Yes.
can hear you.
Okay, thank you.
Thank you.
Good morning, everyone. Again, Christina, the floor is ready for you. Whenever you're ready, you may start your.
Okay, so we have 10 a.m. So let's begin, I think. So good morning, everyone. My name is Kristina Laužikė. I'm from Lithuania Agriculture Science Center, and today I will present our session. So dear key speakers, participants, and guests, today we will hear presentation from Professor Sulan Zhang and Dr. Victoria Vaštakaitė-Kairienė. First of all, I would like to introduce our first key speaker, Professor Sulan Zhang, a professor in soil science and plant nutrition at Northwest A&F University. Her work area are water nutrition and management on Dryland, Kerala, wheat and maize, response of soil fertility to nutrient management. And today her presentation will be attainable water use efficiency and management strategies of dry land, wheat and maize in the China Laos Plateau. So you are welcome, Sulan. Let's work for you.
Thank you. So I share screen. This one. Can you see the slides clearly?
Yes, just do it in a full screen as you can.
Okay. So now it's okay?
Okay, thank you.
Perfect.
Thank you for the introduction. And I'm from College of the Resources and Environment, Northwest A&F University. And I'm very glad to be invited to present our work in the past years. My topic is attainable water use efficiency and management strategy of dryland wheat maize in the Laos Plateau, China. And my presentation will include 3 sections. I first will introduce the current water use efficiency and the attainable water use efficiency. That is what we have adopted the strategies for improving the crop yield and water use efficiency. Then I will have a summary. And this is a global map of rain-fed cropland area worldwide. And roughly 80% of the global agriculture land is under rain-fed agriculture. And this situation in China is about 67%. So the rain-fed agriculture is the key to guaranteeing the food security. But in the semi-arid or arid area, the water shortage is the main limiting factor for crop production. And the Laos Plateau, today, sorry, wait a moment. The Laos Plateau area is this part. Today I focused is a mostly semi-arid area. The precipitation is 300 to 600 millimeter. And the topography is like this. Most area is slope or the ridge and gully area. And we also have the upland, the tableland is about 10% of this arable land. The whole arable land in this area is about almost 17 million hectares. Support the 108 million people. And the groundwater is below 30 to 60 meters. So irrigation is not applicable. And in this area, the soil is quite uniform and very deep. The soil is thickness from 30 to 80 meters. It's very deep, and the soil texture, like the silt content in this size, is 60 to 75%. And the field water capacity also quite similar, from 20 to 22%. So it's very good soil to cultivation. And in the early time, when the economic is not good, so people live in the caves. They take advantage of this deep soil, so they live in caves. And here is abandoned caves. Most people know is mold from the caves. They build the house, but still some people live there. This is the modern caves. The inside they have good facilities, and here you can see is the people still live the caves, and this is the slope land has converted to the terrace land. And in this area, the main cropping is one crop per year, food crop, the wheat, maize, also large area cultivate potato. And because it's the summit area, so water shortage is the problem. So the farmer, they adopt the conservation tillage, like the strong mulching for the wheat and maize field. And also in the recent 10 years, we have our region have the government also encourage for this plastic cover. For this is for spring wheat, and they use the plastic covered soil. Then the top they have put some maybe 1 centimeter soil on the top. And this is for spring maize. This is before sowing. You can see is a large area apply the plastic mulching for produce the spring maize. So the different the tillage and the plastic cover, how they affect the wheat yield. Here we summarize the literature published. We can say the CT is the conventional tillage, and NTRT is the no tillage, reduced tillage, and NTS is the no tillage plus the crop residue cover, and SS subsoiling plus the crop residue. And this is CTS is represent the conventional tillage, then the surface they cover the crop residue. And these three PM, RM, RMS represent the plastic film mulching. And from here we can see these 4 practice or management regimes, they significantly increase the wheat yield and water use efficiency compared with the CT. And also similar for maize. And maize for the plastic cover, they increase the yield most significantly, about 3 tons per hectare compared with the conventional tillage. Also the water use efficiency sometimes is double. And but because of the plastic film, when you cover, they have the residue, the pieces in the soil, they have some negative effect on soil property, they may block the water and the nutrient movement in soil. So there is a pollution. So the people concerned about the pollution. So we also use the meta-analysis to compare the partial cover and the 100% of the full cover of the plastic. We found that these two, they have similar effects on both yield and water use efficiency. So we can apply with partial is okay, not the full cover. And when we estimate what about the highest or attainable water use efficiency in this area, so we use the method developed by the French and Schools from Australia. The scientists, they use this easy way called boundary line. So the boundary line is you plot the yield against the evapotranspiration. Then this line is the highest yield for different ET conditions. And this slope is the attainable water use efficiency. Also like this equation showed the transpiration efficiency. So based on this approach, we estimated the Loess Plateau, the weight yield against the ET, then we got this line is the attainable water use efficiency is 26. And for the maize, we got the 45. This red line for weight this is from world average for the weight, summarized by Australia scientists. And this maize is from United States, is the coal belt. They got this attainable WUE is 38. So why we have higher values? It's because this plastic film mulching. Because this has been reported that plastic film mulching can increase radiation use efficiency. So we know the transpiration efficiency is influenced by the radiation use efficiency. So when you increase radiation use efficiency, you also increase the transpiration use efficiency. That is the main reason. So for this, we know the attainable WUE and also the current, there is a gap. So how we reduce this gap? And then we back to this boundary line method. So this boundary line, if we say this equation, so if we want to increase crop yield, when we need to increase ET. We increase ET, then the yield also increase. This is the first. Then also, we can decrease the soil evaporation. Is this one, then we can increase the transpiration rate. And also, the third is if we can increase this slope. And this maybe can achieved by the breeding program. So you breeding the new varieties with the high transpiration efficiency. And so based on that three principles, so first, in this Loess Plateau, government also encourage and support you transfer the slopeland into the terrace land. Of course, this is a large project. You need the investment, and also in the area from 2009 to 2018, every year we convert the so many hectares from slopeland to the terrace land. And after conversion to the terrace land, we know this we can reduce the surface runoff and increase the rainfall infiltration into the soil. But we can say here for a potato yield, the slopeland you got almost 30 tons per hectare. But after you convert to the terrace land, when the new one, they will be decreased yield because of the soil fertility because you dig the subsurface soil to the cloud layer, you will have the low fertility. But then with the years you cultivated, increase the years, you can say that when the 5 years old periods, they have significant higher yield. And the second is we can design the crop or cropping system matching your rainfall pattern. And for our area, we have winter wheat, you sowing from September, then you harvest in the June, so but the rainfall is less. And if you grow in spring maize, almost they fit this rainfall pattern. So we have tested this difference. And we found if you grow in spring maize, instead of winter wheat, you got 3.7 tons per hectare yield, more yield. And you have similar water consumption. So the ET is similar. It doesn't matter if it's wet year or dry year. And we also estimated, because this Loess Plateau, we have the tableland, about 10% of the whole arable land is about this, West 700,000 hectares. So we can produce 6 million tons more grain for planting maize instead of wheat. And also this is another example from US, the Kansas state. They compare different cropping system. They found that if the winter wheat followed by sorghum, then fallow, and also the winter wheat followed by corn, and then followed by sorghum, then fallow, they have more yield than the winter fallow, continuous winter fallow. So it's more good cropping design, you get improved water use efficiency. And similarly, they also found the water at the sowing time in this two cropping system is better than this continuous wheat. And to increase your ET, so you may have to improve your soil fertility and optimize your nutrient management. Here we have used the long-term experiment to test the different soil fertility, low, medium, high, and what about the water they use. And this is the green season evapotranspiration, ET. And the TW means total available water can be used by the wheat. Which is soil water in 3 meter depth plus the rainfall in growing period. So it's all water source. And we found that the high fertility, they can use about the maximum 80% of the water they can use for produce the wheat. But if you are low fertility, your maximum is less, most cases you less than 60%. So that is, for this condition, the crop yield is not limited by your water, it's by your the nutrient management or your fertility conditions. And we know the water shortage is in most cases is a problem. So how we conserve water. And back to say our rainfall pattern. So winter wheat is growing season is not the rainy season. So the non-growing season, the water also important. Even the spring maize, they match the rainfall, but at the sowing time, the rainfall is not much. So the soil water also important for the germination. So we found that for winter wheat, this is soil water at planting, and the yield is affected by the soil water at planting, also the growing season. And we can see this slope for the soil water at sowing, the slope for each side, they have similar slope. So they both is important for the keep the bit higher yield. And in this case, we apply for the during the fallow time, non-growing season, we use the crop residue cover or plastic film mulching. We can increase the soil water compared with the conventional tillage without any cover. And this is maize wheat, and this is maize. And we also say that if we increase crop yield, we may increase the transpiration efficiency through breeding the new varieties. Here for maize and wheat, we can see the different varieties, their water use efficiency can be very different. Here is the 0.6 and highest can be 1.6 and similar for wheat. So we need to select the drought resistant varieties. Besides the above, the three principles for increased yield, and we also found, or other sites also found, if we modification of water use pattern within the growing season, they also significantly affect the yield. For winter wheat, we can see winter wheat growing yield is significantly and negatively correlated with the ratio between the pre and post anthesis ET, which means when wheat use more water before anthesis, you will have lower yield because the water is the total amount is the fixed. So if your proportion use more, then the left is less. And for maize is opposite from compared with the wheat, because maize they significantly correlated with the evapotranspiration before anthesis. This is because the maize they overall is matched with the rainfall pattern. So the pre-anthesis ET means you have good canopy, and that is important for the yield, because after anthesis, maybe the water is sufficient, not affected. And to adjust or regulate the water use pattern within the growing season, maybe one way we can use the seeding rate to adjust. Here is the winter rate we did a 4-year experiment. And for if you have a low seeding rate, compared with the medium is 25% lower. And if you high, that is 25% higher than the median. So we can say the crop yield, the high seeding rate, not increase the yield, but they significantly increase the water use. And then they have the significantly lower harvest index, and also the significant, not significant, but the lower trend of the water use. So use the right seeding rate also can adjust the water use pattern. Another approach is after you are growing during the crop growing season, then you can take some measure like root pruning. Root pruning is like you use machine. You can, in the early spring, you can cut the plow layer about 20 centimeter depth, then you cut some roots. Then in this way, they can adjust your population or the tailoring of the weight. And with 4 years, we found that yield can increase 7%. Also increase the harvest index and the water use efficiency. And of course, maybe the advanced approach is if we can harvesting water in the non-growing area, then you can store and in the crop growth stage, then you can take the irrigation. That also can significantly affect your crop yield. This is the example from the Eastern Ethiopia. And in our region, Northwest China, we use the plastic rainwater harvesting cellar. So this is relatively cheap, and they can prevent the water percolation. Then you surface, then you also can cover, then you store here, then in the key time for crop, then you provide some water, then you can guarantee the yield. So that's all the approach we used in our area to improve the yield and water use efficiency. So now it's come to the summary. And for improve the semi-arid area, the crop yield and water use efficiency, we need derive or consider the practice at system level. Or like you may have a farm cylinder for time tillage, seeding. You look at the weather forecasting, and if you derive water harvesting or not. And you also can design your farming system. Include the variety you select, or if you have some method you will take during crop growing, and also the what kind of tillage you use, and also of course the soil you management is also very important for the nutrients. And in the long term, you may improve your soil fertility. And so it's a integrated management for improve the yield and water use efficiency. So that's all what I talk. Thank you for your attention.
Thank you, Professor Salan. I look for questions. Maybe someone from our participants have a question, please write. I write it in YouTube where we can see the questions. Maybe anyone has it.
Sorry, I will stop. Maybe I. Oh, there.
So I see there is no questions. Thank you for a very interesting presentation. It's very important nowadays. And now we have a half-hour timeout for our next presentation. Will be at 11 o'clock. So have a small break and see you after half an hour. Thank you, Solan, again.
Thank you.
so we have 2 minutes till 11. And we will begin the next presenter. So hello again, everybody. Hello, dear participants, key speakers, presenters. And now we will have a presentation of senior researcher at the Lithuanian Research Center for Agriculture and Forestry, Viktorija Vaštakaitė-Kairienė. Her main research areas are photophysiology, stress physiology, biochemistry, and post-harvest. Her research is conducted to determine the physiological response of plants to the spectrum photon flux density, photoperiod, and frequency of electric lighting and evaluate crop productivity, contents of secondary metabolites and mineral nutritious, and overall post-harvest quality during the storage. And today she will present a presentation titled of Lighting Strategies for Improved Quality of Leafy Greens Indoors. So here a word for you, Victoria.
So good morning, everyone. Thank you, Christina, for a nice introduction. And also thank you for the organizers for the invitation to give a speech today. We'll share my screen. I hope everyone can see now.
Yes, it's perfect. Thank you.
So as Christina presented, today I will talk about lighting strategies for improved quality of leafy greens indoors. So my presentation will be first about vegetables and their importance as well as their quality. Also challenges of producing vegetables today. I will talk about controlled environment agriculture and artificial lighting, and will present the most recent research on vegetable production indoors. So probably I don't need to say much about vegetables because we all know how they are important for our health, for our balanced diet, as they provide not only the energy for us, but also supply vital nutrients like minerals, vitamins A, B, C, carbohydrates, and proteins. Also in agricultural, meaning vegetable crops give higher yield per unit area as compared to other crops. Vegetables produce from 4 to 5 times more food per unit area when compared to cereals. So it's quite important crops. And most vegetables are of short duration and fit well into many crop rotation systems and crop patterns like intercropping, multiple cropping, and companion cropping. However, we live in a changing environment. We cannot predict what will be the next year. Even we cannot say what will be the weather conditions this year later. So it's very hardly to sustain to prognose what high yield of vegetables we will have in future. In many countries, there are a lot of very limited amount of clean water resources which can be used. There are also big issues with soil erosion, and also, as I mentioned, the crop rotations. And to grow crops, we use a lot of fertilizers, and not all the time they are sufficiently used. And even when we have huge challenges to produce vegetables, we still waste them a lot. The first crop production can be lost during the production of vegetables because of various changing climate conditions and diseases. Later, after the harvest, we can lose the production when we handling them. If the conditions are not suitable for to storage the vegetables, we can lose the big amount. And later, after the handling them, we also do the processing of them, preparing for sale for the retail. And also we can lose a significant amount of the production. And finally, even if the consumer gets vegetables, not all the time it is consumed. So about 30% of vegetables are lost during food supply chain. So the European Commission developed few strategies how to make these challenges, how to cope with these challenges to not lose so much production. So there are two strategies like short food supply chain and farm to fork, which goal are to provide for the consumer the most fresh vegetables and as much fast as can be done. Talking about the quality, first vegetables attract our eyes because we want to eat them. So the appearance is very important. How the vegetable look like, what is the color, what is the shape. Second, we eat them to get the nutrients. So the nutritional value is also one of the most important aspects. When we consume vegetables, we feel texture. Is it soft or is it hard? We also smell. The good smell means a good quality of vegetables. And finally, it's a taste. Even if it has a lot of nutrients or look very nice, it does not mean that it tastes good. There are also other aspects like sustainability. How the production was produced. Was it produced in an environmentally healthy environment? Or recycling, can we use all the parts of vegetables like seeds, for example, for oil? For consumers also it's important the packaging. Is it easy to get, and is it also environmentally friendly? And we want to consume vegetables which are free of chemicals, which are not dirty with pesticides or fungicides. And for getting from farmer to consumers, also transportability, which is a final how all the vegetable look like at the end. So there are a few factors which affect plant production quality. They are external and internal. So external, as I mentioned, it is how we grow them, and what temperature, what was the humidity, was it injured during the harvest or during the post-harvest storage, and if the pathogens disease are affecting also. And as vegetables are plants, it's also internal factors like physiological and biochemical, which determines how crop grow and how much nutrient it has. There are a few strategies how to get and maintain quality. I've mentioned the three main strategies. So first, we have to produce high quality plant species and cultivars. We know that some species or cultivars are more resistant to diseases and the other conditions. Also, the use of technologies which allow to achieve high quality production. And the final strategy would be to follow good practices for post-harvest handling and storage to keep that vegetables fresh. So most of the production today is grown in controlled environment agriculture. It is not a magic place, but it is a method with a certain degree of control over the plant's environmental conditions, with the intention to improve crop yield while minimizing growth variations. So the main factors, environmental factors in controlled environment agriculture are lighting, temperature, carbon dioxide level, relative humidity, moisture content, and nutrient composition. And comparing all these factors allows us to customize the conditions for different crops to increase their productivity, to make them stable to changing climate, and grow them sustainable. And of course, it is important for food safety to keep them fresh against microbiological contaminants. So there are two types of controlled environment systems. First one is like semi-closed environments, like greenhouses or tunnels in the fields. In such systems, we have natural daylight. However, it is also can be not sufficient. So usually the artificial lighting is used at the end of the day or at the beginning of the day, trying to keep the photo period which is optimal for that crop. However, we have fluctuations of temperature, CO2 and humidity, which can be controlled by using technologies like air conditioning systems, cooling systems. The second type of controlled environment is closed systems. Usually they are called like plant factories or vertical farms. Compared to the greenhouses or other semi-closed environments, there is no daylight, so only the electrical lighting sources are used. And also differently from previously mentioned systems, we can control and keep the constant microclimate. We make the exact temperature at day and at night, as well as air humidity and fixed CO2 concentration. However, comparing these two systems, in both we can grow vegetables regardless of the weather or season. We also can use water and fertilizers in a very efficient way. And these systems can be created near the cities, which allows to short the food supply chain and make production cheaper. And in countries which do not have fertile areas and do not have good soil, they also can be developed because of using the hydroponic systems, which gives the sufficient amount of fertilizers for plants. So the main factor in such system is light. Light is the main vital process in plants. For that process, plants need carbon dioxide and water. After they synthesize carbohydrate, glucose, who is a primary metabolite for further reactions in plants. Photosynthesis depends on light intensity, temperature, humidity, and nutrition. So we know that plants, there are a few groups of plants which need longer photoperiod or shorter photoperiod, or they can grow in both scenarios. So they are considered as short and long day plants. And if we are trying to grow long day plants in growth systems like greenhouses, we have to add artificial lighting to increase the photoperiod, but the light intensity would be sufficient for plants. So plants feel the lighting through specific photoreceptors, photosynthetic photoreceptors, which are chlorophyll A and B and carotenoids. However, plants to make photosynthesis process does not need full spectrum of light. We know that the most efficient light which can plant absorb by chlorophylls and carotenoids are in blue and red spectrum. So this process occurs only in that cells which contain chloroplasts. So the leaves are considered as the main organs of photosynthesis. Despite photosynthetic receptors, there are other photomorphogenetic receptors like proteins, which would allow plant to feel and absorb UVA or UVB spectrum, as well as blue, green, red, and far red. So these receptors and the light absorbed by these receptors is used for plants' growth, development, and many metabolic pathways. However, plant use light in different percentages. Only about 80% of lighting is absorbed. About 10% is reflected and 10% is transmitted. Of course, it depends on the leaf shape, also the direction of lighting, and even of plant age. So there are light measurements which are used to get the information about what lighting plants get. So there is like photosynthetic photon flux, where we have 1 micromole of lighting, which is 1 Avogadro constant. For the photosynthetic reactions, we calculate the photosynthetic photon flux density. If we want to compare the energy consumed by the luminaires, we use photosynthetic photon efficacy, and the final how much plant gets per day is calculation of daily light integral. So light emitting diodes are the most popular nowadays, used as row lights. It affords a high level of spectral tuning. They are well known for the electricity to light conversion efficiency and a long lifespan compared to the other lighting sources like fluorescent light or high intensity discharge light. The LEDs can offer the best photosynthetic photon flux density, and this technology develops very fast, and the cost of production will be reduced even further. Also, it's important how we give the light or by light emitting diodes. It can be used like intercanopy light modules or regular light sources from up to plants, or it can be diffused light source. The new systems is like hybrid systems, which can detect the deviation in real time and respond to the dip in sunlight illumination. And compared to the Internet of Things light sources, they can feel if the crop has enough intensity, and we can just turn off or turn off in a certain time. So now I will present the research, photophysiological research, the main results of the most recent projects. where we are working on modeling the light spectrum, plant biofortification, using light as a tool and light photoperiod. So in one of our research, we tried to evaluate how the specific additional wavelengths of lighting affect plant growth, coloration, and nutrients. So we used warm white as a main spectrum, which has a little part of blue and green, and the high part of red light. So as I've mentioned before, blue and red lights are the main light spectrum parts which plant absorb by chlorophylls and carotenoids and used for the photosynthesis process. So we also increased the intensity of our warm light, and in other treatments we added the UVA, blue, green, and red wavelengths. And as you see, by adding such wavelengths, it also changed the light spectrum. And from photos, we can guess that some of the red leaf lettuce were more red, or other treatments were more green. So this research was important because even if we are working with red leaf lettuce cultivar, it does not mean that it will be red. So we have to find the way how to make it red. The biometric measurements showed that additional green light to the warm white spectrum increased the biometric parameters like shoot fresh waved and also dry waved, as well as was quite good to improve leaf width and length. However, the addition of blue light decreased the biometric parameters and the plants were smaller, which mean lower yield of final crop production. The measurements of biochemical compounds showed us that additional UVA lighting, blue and green, increased the content of chlorophylls. Also, as we see that under the additional blue light, lettuce were really red. So it is because of the anthocyanins which were accumulated in the leaves, which gives a color to the plants. And if we are talking about how healthy these lettuce were for humans, we see that blue, green, and red lights were the best to improve the antiradical activity, to cope with reactive oxygen species, which are negative for our health. And we also evaluated how these lettuce can keep the accumulated metabolites after 1 week. However, we found that blue light increased a lot the contents of these metabolites, and they were stable at the end. But red light, which didn't show such good response to the lighting at harvest day, at the end, after the 7 days, the content of metabolites was similar to those lettuce which were grown under the blue lighting. So in another research, we are working with plant biofortification and use lighting as a tool to improve the uptake of nutrients, specifically of micronutrients, iron, selenium, and zinc. So biofortification or biological fortification refers to the nutritional enhanced food crops with increased bioavailability to the human population that are developed and grown using modern biotechnological techniques, conventional plant breeding, and agronomic practices. So the research was funded by Research Council of Lithuania. And we, as I mentioned, trying to increase the essential trace elements in leafy vegetables to make them healthier for humans to consume. And this project, we are working with plant hydroponic systems, which are various types. The difference is that we don't grow plants in the soil. We start seeding them in the rock wool and later transfer to the hydroponic system with mineral nutrient solution. So such a way allow us to decide the concentrations of minerals and use them very efficiently. Our results showed from the research in which we investigated the different ratios of red and blue lighting. When the first ratio was the most optimal, considered the most optimal for plants when the blue light was 10% and the red was 90%. On second treatment, we increased the intensity of blue lights up to 25% compared to the red light. And in the third treatment, the blue intensity was the highest, and only about 25% was of red. And we added different doses to the hydroponic solution of iron from 2 to 15 ppm, and we get the results that considered the optimal conditions of 10% of blue and 90% of red at 2 ppm and 5 ppm were sufficient for spinach growth and accumulation of chlorophyll. However, we got the same result when we increased blue light intensity just a little, up to 25%. However, when we increased blue intensity made it the main part of light in whole spectrum, it was the most efficient way to increase iron content, chlorophyll, and radical activity, and other uptakes besides iron of macro and micronutrients. And it did not depend on how much iron we put in the hydroponic solution most. We also worked with mustard microgreens, which are very young plants, which have only one pair of true leaves. And in this research, we added additional green light. And we found in previous research that 15 ppm of iron is not used most efficient. When we calculated the final concentration of iron in plant and iron and nutrient solution, we saw that up to 5 ppm was used efficiently. So we did not continue the research with 15 ppm of iron. So we see that when we have optimal spectrum of blue and red at 5 ppm, we increased the iron concentration. When we added a bit green and a lot of green at 5 ppm, it also was efficient for the uptake of iron. Talking about growth, the huge part of green, which is equal to the red light, and blue light was lower, and 2 ppm was the most efficient to increase the biomass of mustard microgreens. Talking about sugar is also was the most efficient. Vitamin E or tocopherols were accumulated also at the lower dose of iron. And then the green light was added to the spectrum. And the antiradical activity was the highest when we add 5 ppm of dose, but there was no green light in spectrum. So the similar results of vitamin E and antiradical activity were also achieved when we grow baby leaf lettuce 3 to 4 weeks old. So we can think that such similar response of 2 different species and 2 different growth stages plants might be similar to other plants also. And talking about growth conditions, the higher dose of iron and the addition of a bit green and the similar amount green like blue and lower red intensity was the most optimal. Of course, we are working with iron. It is interesting how much iron is in lettuce. So green light was efficient of iron only when it was added a small amount compared to red and blue light. And the content of sugars were accumulated when we had equal parts of green and red and lower part of blue light in spectrum. Another work we are working on is about plant photoperiod. It's also a project funded by Research Council of Lithuania and together with European funding. And in this project, we are trying to get information about photophysiological response and production of leafy vegetables indoors under different light and dark conditions. So in this experiment, we were growing plants under the blue, green, and red lighting for 16 hours. And after the 16 hours, we increased the photoperiod, but only leaving the blue light turned on. We tested 2 different intensities of blue light as the main source of lighting at the end of the day for 4 hours. And we found that such way, when we leave only one wavelength at the end, helped us to increase the leaf length and leaf width of lettuce. However, even if the leaves were longer and wider, it did not significantly affect fresh wave. It just increased the shoot length, but the wave was similar, which showed us that leaves were weaker. And talking about how the metabolic response was, we found that additional blue light at the end of the day at lower intensity increased the content of proline, which allow us to think that plants were stressed, probably because of having only one light source of blue light, and it was 30 micromoles were not so enough for plants compared to the 60 micromoles. And we see that also the antiradical activity increased under the same treatment together with proline. So yes, it allows us to think that plants were stressed. However, considering about total phenolic content, we see that it most decreased under the blue light intensity at 60 micromoles when it was used as a sole light source at the end of the day. At the end of my speech, just few farming ideas, how we can grow plants, vegetables at home. The producers create small systems according to results of different researchers in various countries, trying to find the most optimal spectrum. But we see that it might be quite difficult to achieve, as all plant species, even the same species cultivars, react to lighting very differently. So thank you for your attention. And also thank you for all my colleagues who helped to achieve these results I've presented today.
Thank you very much, Victoria. And now we have one question for you, and I'll try to read it from the page. And in your research on light effects in the plant biofortification project, you control a number of other factors, like, as you mentioned, minerals in hydroponic solution. But what importance does level of carbon dioxide in the environment play for nutritional values? And how did you control the carbon dioxide variety in the environmental?
Thank you for your question. During this research, the carbon dioxide environment was maintained. It means that in all experiments we were working on, that was the same carbon dioxide concentration. However, it is a good idea for the future research. Thank you.
Thank you for your answer. Maybe we have some more questions. If you have any question, please write. I'm still waiting for it. And now, thank you, Dr. Victoria, your presentation is really interesting, and I think it's can be used for a future research, even eventually for a post-harvest, which is very important nowadays. And thank you very much.
Thank you.
And now we have no questions, but I want to present you some rewards we have done for our PhD students. Just a second. And so we have some papers presented in this conference for the Lithuania Research Center for Agriculture and Forestry PhD students, and we have the 3 best papers which they prepared. And now I want to present them. So the first place goes to Muhammad Ayaz, which are a PhD student from 2019, and he prepared a really good paper, and congratulations for a 3rd place. Second place goes to Ruta Sutuliene. She's a last year PhD student, and congratulations and good luck to this year for presenting your PhD. And the first place, Anna Doviliuchkite, congratulations. You are the best this year, and I want to say big lucky for end of this year, and good luck to present your PhD, because this is the last year for her PhD student. So congratulations for all participants. Congratulations for our papers winners, and I hope that next year we will have more papers. And I'm very glad that our students are preparing really high quality papers, which can be printed in the high quality journals. So thank you today. And before we are leaving, I would like to remember that after 20 minutes at 12 o'clock, all environmental section participants must be near their stands and answer all questions. So good luck and have a nice day.